Okay, hi everyone. Thanks for joining us this afternoon or morning or night, whatever time it is, wherever you are. We're glad to have you guys here. We have Bruce Stevens here. He is a business development manager with Fluence. He's got a very long career in water purification, and he's going to share some details and information on the MABR technology here with Fluence. So I'm going to let Bruce take it away to get started for the case of time, and we'll have some Q&A at the end. Thanks so much.
Thanks, Jessica. Welcome, everyone. I look forward to hoping to share some interesting information that we've applied our technology to, and hopefully you can take something away from our meeting today. As Jessica alluded, I've been in this business for many, many years doing everything from sludge and biosolids to drying technology and BNR and instrumentation and all sorts of fun things. So I wish you all a long and enjoyable career yourselves. I used to have long red hair. As you can see, that I don't have that anymore after becoming a WEF Life member recently, and still enjoying it. I still think I'm 29. So let's talk about what we're doing for fun here at Fluence right now. So MABR in general, we use this process diagram to generally compare our process to other forms of BNR, ENR. It's a simple 3-zone process. We use everybody uses pre-treatment at the beginning of the plant to take out fog and screenings and other particulates, grit. And then we go immediately to a zone, an anaerobic zone, where we mix the RAS from the process with the incoming raw wastewater. It's an important step in our process design. We like to use that to make sure there's no oxygen whatsoever in there, eliminate a lot of the issues with soluble BOD that can occur, and absorb all that soluble BOD into the RAS so that when it goes into the anoxic zone, the biomass in there is focused on doing one thing and one thing only. So the second stage after a short contact time is the anoxic zone, where the MABR towers sit, and that usually is designed to focus on ammonia removal and begin the nitrogen removal process. And then after that, we go through a low DO aerobic zone where we can do simultaneous nitrification, denitrification, before we go into a clarifier where we have a very nice settling sludge with a low SVI, usually less than 100 milliliters per gram, very, very good settling sludge, and then we split it and return it back to the front of the plant. Obviously, afterwards, part of the system, you always need a clarifier if you're just going to discharge and make a relatively clean effluent, 30-30, 20-20. If you're going to reuse, you can either do it with clarifiers and filters after them, media filters or cloth disc filters for the sake of example, or you can go to some form of membrane, whether it's an MBR cassette or another style of membrane if you're going to go to the reuse and get rid of most of the excess TSS and remove a lot of the BOD. So we don't always supply that part of the process, but we like to focus on the anoxic zone, the MABR zone, and the SND, so we can control it and make sure that the process operates properly. Now, when we talk about MABRs, initially, when people haven't heard much about them before, there's some confusion about the membrane and what it actually does. So we use this slide just as a quick clarification step to make people understand that it's a membrane, but it's not meant to separate liquids and solids like we do with an MBR, with a flat sheet membrane or a ceramic media membrane, any kind of membrane that we use to separate solids from liquids. That's not what we're doing. Our membrane is the basis for a biofilm process, and it's really focused on separating oxygen, pure oxygen, from the atmospheric air that we use to feed the biofilm reactor. So all we allow through the membrane is pure oxygen. Any nitrogen that's in the air and CO2 gets rejected and sent away. So having said that, everybody's familiar with different types of diffusers. This slide just gives you a relatively good feel for the amount of energy that we use in the different types of diffusers. For many years, we used surface aerators, the standard Metcalf and Eddy's book for years and years and years. And then, in the 60s and 70s, we improved and went to coarse bubble diffusers. We saved a little bit of energy. The same in the 80s and the 90s with fine bubble diffusers. We started saving even more energy going to that design. But one of the issues is still diffusing oxygen from the bubbles through the air, through the liquid phase, and then into the biomass. That's the one thing that we do very efficiently with the Fluence MABR system, and it's an interesting process. So we'll get into that in a little bit more detail in the next slide. So MABR technologies have been around for 20, 25 years. Conceptually, they came up at the end of the 20th century, and now that we're in the 21st, we've really started to develop them, commercialize them, and many have been installed over the last 10 to 12 years. There's two different kinds of oxygen transfer devices. One of them is the tubular filament, what we call weeds, or our flat sheet design, which is call it a jelly roll. It looks similar to one. It's a good nickname, a good way to describe it. There's many plants installed worldwide now over the last 10 or 12 years. So we have a breadth of experience, everything from 5,000 gallons a day up to about 20 million gallons a day currently operating. Cold weather, warm weather, tropical, mountain, seacoast, middle of the country, everything all over the world. We've got a lot of these overseas in the Far East, and we've got more installed in the Caribbean and in America. We're working on some in Canada. We're working on others in other parts of the world as well, where they can impact and do a good job. So the technology that we're focused on is our spiral roll design, and that membrane is a unique membrane that we apply and use. We make a sandwich out of it, and that sandwich is two pieces of the membrane with a spacer in between, and that's seam welded together all the way around the membrane. Now, these membranes are 1 meter high or wide by 300 meters long, so 900 feet approximately. And when we wind them up, they become about 2 meters in diameter, completely wound up with the spacer that we add to allow the water to go between the layers and get to the membrane where the air comes out and the biofilm grow. So when you do a close-up look, the membrane itself is a very, very thin sheet, and it's got a special coating on it that allows just the pure oxygen to come through from the air supply. A biofilm, a very thin layer of biofilm, about 200 nanometers thick, grows on the outside of it on the water side, and that's composed mostly of autotrophs. The autotrophs obviously are focused on removing ammonia and denitrifying, nitritation as well. So that's their focus, and we'll talk about that in a little bit more detail next. So when the system operates to generate the autotrophic biofilm, we seed the membranes when we first get started, and they're self-sustaining. That thin biofilm forms after a few days on the membrane, and then we're seeded. So what happens is the biomass absorbs the oxygen from the other side of the membrane, from the air side, and consumes the ammonia right in the film itself, releasing nitrate and nitrite, which go into the mixed liquor that's outside in the bulk fluid. Now, as we all know, that then starts to be attacked by heterogeneous heterotrophic bacteria that are in the complete mix activated sludge in the main process, and that uses the BOD, takes the free oxygen and the nitrate, and then converts it into nitrogen gas. So that goes off, and the process moves continuously into the next zone where it completes the treatment. The spiral flat sheet is unique. We're the only manufacturer in the world that fabricates it and uses it in this application. And we focused a lot of research and development back in the late 2000s, early 2010 range before we commercialized it. The nitrifying bacteria that colonize the membrane are composed of 10, 12, 15 different genera and species of autotrophs that we've done a fair amount of research on, and they're doing just their job, is just focused right on the ammonia removal and converting that nitrate in the anoxic zone. So as you can see up and below, we have the water spacer in between. We only push 1 psi of air in there with regenerative blowers. So it's a very low pressure application, which saves energy in your process overall. That's one of the key aspects of our design. That low pressure air is just enough to get the oxygen molecules into the biofilm, and there's an immediate uptake and advantage where we don't have to go through the liquid layer to get the oxygen into solution and then into the biomass. It goes right into the biomass directly, and it's very effective in its overall energy efficiency and use. So when we stack these and put them into actual practice, what we're going to do in the in concrete tanks when we're doing retrofits is we'll build these in towers and arrange them in this shape, as you can see. We have a frame that we put them on. We have connections for air piping. We have a coarse bubble mixing system that we include with the unit to circulate the contents of the tank. We began making these modules over in Israel in 2012 and continue to make them there, as well as at another factory we opened in 2016, early 2017 in Shanghai. There's been a lot of sales of these units in the Far East. It's a very effective energy-driven area, so they've been very lucky to put in close to 300 systems in that region of the world. So when we look at the MABR tower, we can go up to 4 spiral membranes in overall height, which will get you into a tank volume of about 5.2 meters or 16 feet of liquid depth. We can put one in if it's a very shallow tank, like an old RBC tank that you want to reuse. A couple of them can go into an old trickling filter type of tank, which is 8 or 9 feet of liquid depth in a trickling filter. And then, shallow activated sludge might be 10, 11, 12 feet deep, and we can stick 3 towers in there. And in a bigger, deeper tank, which is, 15, 16 feet side water depth, we can put 4 on top of those. So this has been the workhorse that we've been using for the last 10, 12 years. And we continue to do research and development. And over the last 2 years, we've tried to optimize the design and increase the packing density of the system. And the work has led us to our new 2nd generation bioval design, which gives us about 50% more value per square foot of membrane surface area in those rectangular tanks that we're going to be retrofitting. So it's just an elongated spiral. It has two posts to feed the air and remove the air from the center, and it's a little bit more effective that way. This is a T4 tower showing 8 spirals together in one frame. It's about 7.5, 8 feet long by 6.5 feet wide. And this is literally, 5.2 meters tall at the top. It's a much better fit in concrete tanks than the circular design, which had, more dead space. So this has enabled us to get better fit in smaller tank volumes overall. So now we're going to talk about our MABR process and the Nitro process as well. Talk about retrofit projects, what we're looking for, what we think we can help best with our clients and consulting firms, and areas that are best to utilize this technology when you're out there evaluating different options. So we do a lot of small plants that are below 1,000 cubic meters per day, less than a quarter MGD in steel containerized systems. But in concrete, we really sort of look there around 250,000 gallons a day as the starting point to do a concrete system where it becomes more cost effective. And to date, there are systems out there that are upwards of 20 MGD. So we're stretching it a little bit. We've looked at 30 MGD plants. It doesn't mean we can't go larger and higher flows, but we've sort of focused on that for now and try to keep implementing the technology wherever we can. We also look at plants that have significant side stream loadings from the anaerobic digestion process, aerobic digesters, where there's a lot of ammonia coming back to the head of the plant, which can cause issues with the main process design. And we can do it in existing anoxic basins. We can retrofit, put baffles in, optimize the facility as best possible, use the existing tankage, and try and avoid adding new tanks, which is a big cost, as we all know, especially today with the cost of fuel, excavation, the risk involved, pouring concrete, rebar costs. Everything's been going crazy, and that cost of adding new tankage is it can be enormous and a deal killer. So we try and do as much as we can with it. One nice advantage of this process is you may have noticed in the process flow diagram, we don't have internal nitrate recirculation pumps. We don't need them in this layout. So we're saving a bit of energy by just a single pass process. It's a very robust biofilm, and it'll last for many, many years once it's installed and operational. First, we're going to talk about Nitro, which is our side stream process using MABR technology. It is a shortcut nitrogen removal system. We've done quite a bit of testing over the last 5-7 years with it. And we're looking at several full-scale facilities right now to implement it at. Obviously, places that have anaerobic digestion and co-digestion, places where composting is done, where there's runoff from the composting pads, swine or cow farms where there's a high degree of ammonia, and fertilizer fabrication facilities, things like that. So keep it in mind for high doses, high side stream loads. So it's still a nitro process, is a biofilm only process. It's a single step, single tank where it goes through nitritation and then denitritation. We're just using AOBs to create nitrite and convert that ammonia from that form into the nitrite form, and then let it go up in nitrite gas, nitrogen gas, as a quick shortcut path and reduce the energy impact. We're looking for small streams with only 1-2% of the plant's flow, but up to 25% of the loading. That's the place to do it. As you can see in this process step, when you take the clarifier and waste solids to biosolids treatment and do anaerobic digestion, what we're doing is we're taking that supernate and that filtrate that comes off the dewatering before it goes to solid waste or composting or landfilling or sludge drying, and we're recycling it back to the head of the plant. And that's where we install Nitro, right there. The real good news is that we get a lot of nitrate oxygen as a result, which then goes back to the head of the facility where we're doing the anaerobic zone and the anoxic zone. And that's where we feed it back into that anoxic zone where there's a lot of free oxygen to take up in the downstream process. So this is a case study of a facility we're working with a consulting firm on to upgrade a plant. Land's very expensive. It's going to be a big footprint expansion if they did conventional. So being able to reuse the existing tankage for aerobic, anoxic, simultaneous night denight is very important in the opportunity. And they also have the potential to use a nitro process for the side stream load, because they do have anaerobic digesters and all that filtrate from the biosolids. This is just a quick overview of the facility. SUBRE is our process, the submerged biological reactor system that we use for the MABRs. So that will be retrofitted into the existing aerobic tankage, and then we'll have our low DO SND zone after the MABR section. And then on the anaerobic digester, we'll insert nitro in the side stream. And that's basically taken, a high side stream load of ammonia, in this case, 1,300 milligrams per liter, and taking 90% of it and knocking it away. So the effluent will be less than 100 milligrams per liter with that high nitrate oxygen load that we can recycle and save energy in the plant. So that's just one example of how we do it. When we start looking at complete mix activated sludge applications in the mainstream plant, we sort of look at the flexibility of the process and how it's best utilized to design a plant and upgrade things. So when you consider, you can do a lot of things with an MLE process that we can also do with our process design using MABRs. What is the real advantage to us is the smaller aeration basin, fewer diffusers, a more compact footprint. And that's the key advantage with using MABRs is you can take up to about 40, 45, 50% of the ammonia nitrogen load out of the plant, depending on how many MABR towers or zones you put in to the beginning of the facility, and then reduce the volume of the aerobic SND side. So that's the pure advantage of it, and that's the way we like to try and optimize it for all of our clients. This is an example of a small plant we're under evaluation for. It's a 1 MGD facility with a high wet weather flow, 4.5 MGD peak, and it was designed only for BOD and TSS. So the new flow is going to be 1.25 MGD, and it's going to require ammonia and nitrogen removal after the upgrade. So Arcadis did a study on this plant, and it confirms what we all know. 60% of the energy consumed is secondary treatment. So it's a big number that we're going to be able to hopefully help them with and reduce significantly with an energy efficient process like MABR, especially in areas where there's high electricity rates. You want to look at this for that reason alone. And in other areas, it's fitting into the existing tankage, which we'll discuss here in a second. So in this type of facility, what we're looking at doing is taking they're going to retain the existing primary clarifiers and then go into the secondary treatment, which is existing now is submerged biological contactors in these 2 4-stage trains. So there's rotating submerged biological contactors in there. It's a side water depth of about 13 feet. And what we're going to do is convert the first section to an anaerobic selector and the MABR zone, and then go find bubble SND in the back half. So that's our first cut at this. The secondary clarifiers remain. They're in good shape. Everything's fine. And we took a look at the unit in more detail. Physically, it's a good fit for the MABR towers, the new design. We can fit several units across the width of each basin. We could continue in the future to add more in the second basin and or the third if they ever decided to get down to very, very low nutrient removal limits. But for now, one of the issues is running BioWin because of the cold winter design temperature for nitrification. It also shows a need for more tankage than exists for aerobic treatment. So in this case, it looks like we could need an additional 400,000 gallons of reactor space to make this conversion work properly by cross-checking it with BioWin and assuming that temperature of 10 degrees C during the winter is going to be the limiting factor down the road. So it's important to check that, make sure that these fit properly. If you can't, then you might get stuck having to add existing tankage to it, add more tankage to the existing, I should say. And in this case, luckily, there's a lot of space right here in between the 2 clarifiers. So it might be a very good retrofit overall to do it this way and minimize the investment in the MABR section, but remove the rest of the SBCs, get them out, and use fine bubble aeration, which is relatively cost effective for the rest of the plant, but run it in a low DO mode at 0.75, 0.65 DO, where we get simultaneous night D-night, and consume the rest of the BOD before it goes to the clarifiers. This is another case study of a larger plant, similarly short HRT. It's a high rate BOD removal plant, only 4.5 hours total HRT. It's landlocked as well. So some big loads in it because it is a 30 MGD average day flow, max month flow, I should say. And peak wet weather flow is 58 MGD. So there's that to deal with too, which is great because the biofilm on the MABR towers is very robust and it stays even though there might be higher flows going through the process. In this case, when we look at the side stream load, we notice that the ammonia load is not very high. So there's no anaerobic digestion here. There's no need for nitro in this package. So we're focusing on the mainstream only and trying to figure out how to retrofit these existing tanks. So this is where you bring your Dick Tracy watch and start looking at things and trying to figure out what the best fit is for the existing facility and compare a couple of 3 different types of Lego blocks and how you can fit them into these square holes with round pegs. In our case, it was fairly straightforward with this U-shaped design. The flow comes in from the main channel, goes through 2 tanks and then through the last 2 and then back out. And the system will have, excuse me, an anaerobic zone like we always have, and then the anoxic zone with all the MABR towers before we go into a low-level SND zone for low DO for the simultaneous night D-night. After these aeration basins, there's 6 sets of these in parallel. We go into secondary clarifiers, which we'll see in 1 second on the next slide. So this is a look at the overall plant layout. You're sandwiched between this marina where all the rich people have their boats. That's not going to move. There's some industry over here, which is not going to move. Housing up behind it, and the water right next to us. So there's really not a lot of room here. They're going to be implementing an upgrade to the first section, which is the primary clarifiers, and doing some innovative things up here before they go and upgrade the aerobic system in the next phase in a few years. So what we did is we looked at this, took a little innovation out and figured the volumes that we had in these tanks. And there's just, similarly, there's not enough room to do complete ammonification. And we don't believe there's any process that can make that work. It's not magic. That conversion of ammonia to nitrate just takes time, and at these low winter temperatures that we're struck with, to make the TN removal to get down to less than 5 total nitrogen in the future permit, it's going to be difficult. So we looked at it, and we can see in the secondary clarifier trains, there's 3 trains that run back this way towards the effluent chlorine contact tanks up here after the primary aeration basins feed down a flume and across all 3 tanks. So it's our thought these are 11, 12 feet deep, so we can put T3 towers in this first half of the secondary clarifiers. And constructability wise, I think we can do them one at a time and retrofit these. And our plan is to put MBRs, membrane bioreactor cassettes, in the back half of this to act as the clarifiers. And then by raising the mixed liquor to 8,000 milligrams per liter, the solution works in BioWin after checking it. It's a good fit. And it'll handle the 30 MGD, and the MBRs are sized to handle the 58 MGD peak flow. So this could be a really good way to save money and not have to dig any new tanks. One thing that they're going to do, like I said up front, in the existing tankage above us, they're going to convert the primaries to cloth disc filtration, new grit screening improvements in phase 1. They're going to do a full-scale pilot in phase 2 at this facility. So one of these process trains is going to get retrofitted in 2025 or 2026 when they get to doing that, to prove out the MABR concept. The MBR zones we looked at again and thought there is room here right on the edge of the existing parking lot in the marina. It might be possible to steal a little bit of room to put a new clarifier in there and a new MBR zone initially, which would make the constructability of these 3 other clarifiers much easier from a staging standpoint. So just something to think about and consider when you're looking at upgrades to facilities that are landlocked and very tight to work in, like this one. So since that design temperature is so low, the TN requirement is less than 5 milligrams per liter total year round, we're going to be looking at doing a pilot system, getting it installed, operational in early 2025, hopefully. And then from there, run it for 9 to 12 months, get a bunch of data on it, prove the concept out, and then report that data back. We just did some cost estimates for 6 months worth of cost, and then we have to look at the pilot equipment itself to add to that. This is a picture of one of our small package plants, which is rated for 10,000 gallons per day for BNR. This is at a location in New Mexico at a facility which only has that much flow, but it's the same size container. It's a 40-footer, it's a 10 by 10 rectangle, and this is an insulated container that would be used as the pilot for the full-scale design. Last case study we're going to go over is another plant that's got to do an upgrade from 0.75 MGD to 1.25. And they have BNR right now. They have a 4-stage Bardenfo process, but they have to go to ENR and meet a more stringent permit. So this is the existing facility. The MABR technology has been considered along with D-night filtration upgrades and MBR as a completely retrofitted process as well. A closer look at the plant schematic. Flow comes in down here, goes through grit screenings, pretreatment, and then into EQ, where it then flows down underground to the existing fermenter zone. Like I said, this is a 4-stage Barden flow, and then it goes to the first anoxic tanks, which are right here, and then the secondary anoxic tanks and the aerobic tanks, and then the secondary anoxic tanks here before going into the clarifiers. Then there's actually existing tertiary filters, old travel and bridge filter over here before they go to chlorine contact, dechlor, and then out to the bay. So the intent here is to evaluate and decide what the best value they're going to get for their buck when they do the upgrade. These are the costs from the PER. You can see the MBR cost in the first zone, the denitrification and phosphorus removal filter in the second zone, and then the MABR down here. The next slide will give you a better view of what the process permit layout is looking at. The existing flow, like I said, comes through EQ and then through the fermenter before it goes here into the MABRs. And then we're going to convert these into simultaneous D-night tanks before it goes to the existing clarifiers. And those are going to be upgraded as well as part of the project. So the engineer, in this case, put together the present worth analysis for the three for a cost comparison. And as you can see, MBR, the first one, comes in very high at $30 million, $31 million almost. Alternative two, the denitrification filter came in at $19,300,000 for a 20-year present worth. And the MABR came in at just over 21 at 21.5. So similar range, but this one is very expensive and more difficult to operate and maintain too. Cost alternates were considered. The present worth was one portion of it, the operations value, the maintenance value, and the constructability and implementation were all weighted by the team that did the review. And alternative 2, 3, and 4 were rated with this point level scale. So the MBR did come out the lowest rated. The D-night filter came out second, and the MABR was the highest rated in this process and was selected for the upgrade to the plant. So the final PER has been submitted for approval. It just came back. We are in the process of putting a pilot test container together and getting it delivered this spring to the site. They just want to see it work for 6 months, get some cold weather and some warm weather data to prove that it'll reach the TN limit of 3 total nitrogen during the summer and meet the low level winter as best it can. This is a cutaway of the pilot plant, the 10,000 gallon per day a spiral facility. There's one MABR tower in it, the aerobic zone next to it before the clarifier. And then we also have in this facility media filters in case we go to tertiary level. In this case, we're just going to use the clarifiers because we're not required to do the filtration for the final process step. They elected to go with cloth disc filters when they retrofit the old traveling bridge facility. So that'll be what they do here instead of media filtration. So with that, I'd like to encourage you to keep in touch with us. Give me a call directly if I can be of help, answer any questions, do any evaluations for you, and look forward to questions you may have right now as we develop further interest in the technology and help you implement it for your favorite clients and tough facilities to do upgrades to with these new permits that are coming out. Thank you very much.
Awesome. Thanks, Bruce. We can open up the floor now to any questions. I see there's been some questions coming through the chat that I've had answers to them, but does anybody else have any questions? They can feel free to put them in the chat and then we can address them. It looks like we've got a question. Are you combining the MABR with your Tipton plants?
Yes, as a matter of fact, we are. We have a design that we've generated with the Tipton design, which is a built in America, heavy gauge steel, prefabricated extended aeration plant system that we've used for years for many facilities around the world. That design is what we call a turbo Tipton. So we've included an anaerobic selector zone in it, added the towers that fit in that 10, 11, 12-foot deep facility. So we can put as much as possible into the front end of that zone and upgrade that type of plant to a nitrogen removal plant that operates very seamlessly without a lot of effort on the operator's part. And those go up to about 300,000 gallons a day because they are field welded, field connected, and we can stack multiple units side by side by side. So you can have a bigger facility in the end with those.
All right, Bruce, we got another one. How do you keep the biofilm healthy and working?
One of the things I didn't actually mention in detail, let me just scroll back here to show you something that makes it a little easier to understand, is when we work with the towers, they don't just sit inside the tank idly waiting for flow to come through. Underneath these, we have coarse bubble perforated pipe engineered grids. So every 30 to 45 minutes, we turn the coarse bubble on for 20 to 30 seconds, which gives it a blast of air, and that rises through the tower, through the spirals. It carries food. It creates an airlift effect, so it brings food around the tanks, around the towers, and then up through the middle, close to the membrane, where the ammonia then is taken away by the biofilm, and the heterotrophs can start using the nitrate that's converted in the process. So the DO is not non-existent in that tank. It's still an anoxic tank. That coarse bubble airlift just happens, like I said, every 30 minutes or so, and it just circulates the whole tank quickly, gives it turnover, gives food to the biofilm. There's a natural sloughing of the biofilm. We don't have a scouring kind of system of any sort to keep it clean. We haven't experienced excess growth. We haven't run into problems of any kind. So that's just our mechanism, our technique. We think the anaerobic selector in the front of the system really helps quite a bit by taking up all that soluble BOD before it gets into the anoxic zone, where the autotrophs can really focus on the nitrogen removal and the ammonia conversion. Good question.
Bruce, another question. Can you explain a little the benefits of MABR versus other attached growth processes like MBBR?
Yes, relatively easy. Side by side, they're considering MBBR, MBR, A squared O, and I believe another type of process to go along with MABR is one of the options they could use. Obviously, when you look at those other ones, there's different energy levels that are required to maintain those and operate them. The biofilm in our system is very robust. The advantage we have is really the energy efficiency, the lower OPEX when you compare to those facilities that require a lot more air to keep everything mixed all the time, whether it's the MBBR media or keeping the MBR cassettes cleaned and scoured properly in an MBR process, or an A squared O, where you just got to keep everything moving around the tank and make sure it's completely mixed. So complete mix activated sludge, even though it's similar to what we're doing, is a more energy intensive process. And that's the big advantage, using that low pressure air to get the oxygen transfer into the biofilm. And we can really reduce the overall energy compared to those, call them traditional processes, by 40 to 50% total. So it's a big number to look at when you consider MABR.
Okay, Bruce, another question we have is, what's the procedure to remove and inspect the MABR?
There is no removal of the MABR towers. That's not part of our process requirement or design. The systems, once they're fixed in place, are either attached to the floor of the tankage or the wall. So the whole rack is set in there. Our experience in the last 10 years indicates there's no degradation of the membrane, the rack assembly, the entire spiral. The biofilm is robust. It's very thin. It stays in that shape based on the feed, the forward flow, the regular mixing that we put into the zone. So we look at it as we give a 15-year guarantee on the membranes themselves, on the MABRs, but we don't expect to need to honor that warranty because we believe they're going to last 20 to 25 years. So if they go as far as an old RBC type system goes, a lot of those older systems were, that some type of attached growth media or a trickling filter type of design. We're much more efficient. It remains in place. You don't take it out and play with it and fix it. There's no maintenance to do on it. So in this case, we expect it's going to be, end of life at 20 to 25 years before they're physically, you have to drain a tank, take them out, replace them with new technology.
Okay, Bruce. It says you mentioned pure O2. Are you using oxygen generator or are the bacteria only using the oxygen? How do you guarantee the bugs use all the oxygen?
So when you look at the membrane, as I said, it's set up to get back to this one, only allow the oxygen molecule to pass through that. It's a semi-permeable fabric. So the biofilm growing on the opposite side of it absorbs only pure oxygen. The nitrogen gas that's in the ambient air and the CO2 that's in the ambient air and any excess oxygen that isn't consumed by the bacteria flows out and up to atmosphere. So that's the way the system works. It's very low pressure. It's just pushing through there at 1 psi-G, and it's just enough for the biomass to use the pure oxygen only. So that's why it's very efficient. We're not really wasting a lot of it. We're not generating pure oxygen. We're just separating the air into that two stream, the reject stream and the pure oxygen feeding into the biofilm. I hope that explains it.
Great. That's all I see for questions. Oh, it looks like one more. Can this system work with high loads of FOG or calcium? Or are there limits?
Yeah, there are definitely limits. When we talk about the pre-treatment required, we have specific design limits for the technology. So when you look at a plant like we have here before, let me just scroll down one or two. All these facilities have regular pre-treatment going in up front, and that includes grit removal and fog removal. We allow a maximum of I think it's 50 parts per million of fog to pass through. But then we have a fine screen, which is below 2 millimeters, so it's 1.5 millimeter or lower screen, which takes out any real large particulate TSS and rejects it to waste and digestion. And that flow that comes through is then clean of all that trash that would otherwise get stuck in the MABR towers. We don't want that in there. Just like an MBR, a regular membrane bioreactor plant with cassettes, you don't want all that kind of trash. Everybody uses fine screens in those as well for this purpose. And we really want to avoid getting the fats, oils, and greases in there because it will foul the membrane surface, and we don't want that there.
Okay, Bruce. This one says, thanks for the answer on the O2. What would you guess the oxygen transfer efficiency is? Have you measured the vent gases or completed mass balance in BioWin?
I have not personally done that work. Our engineering department has. We don't generally get into that level of detail with the process design. If we do get to a certain level where that interest is significant, we can address it. But these are the kind of numbers that we share generally for overall efficiency of our process, because this is where the real energy savings comes in between this type of membrane and this type of membrane, where you have to get the oxygen, the air bubble, which only contains 20% oxygen. You have to get that through the water and then into the biomass itself, so it can use the oxygen. Ours is going directly into the biofilm, so that's where the inherent energy efficiency savings is. We don't look at it as a pure oxygen efficiency ratio, or we don't calculate it in BioWind. We do it on a BioWind design basis for the bulk airflow, and know what the capability is of the MABRs in a loading standpoint. Like, we can tell you that 5 grams of ammonia per square meter of biofilm area is what we use for design criteria. At 20 degrees C, at different temperatures, we change that. So we can get into more detail if we get beyond a preliminary evaluation into a more rigorous final design, and flesh that out for you specifically for a project.
So that's all the questions I see so far. If anybody else has anything they want to add, you can do it now, or you can always shoot an email over to the team.
Wonderful. Thanks for all the good questions. Thanks for your attention. I appreciate the opportunity to share this with you today. And like we said, please get in touch with us if we can help you do some evaluations for your clients and your facilities.
Thanks, Bruce.
You're welcome. Take care, everybody. Have a great rest of your week.